very good morning, very good afternoon, and very good evening to all the participants joining from the respective places for this lecture series on conservation of heritage sites, where the first lecture will be delivered by Professor Guido Gottardi from University of Bologna, Italy. We have dignitaries, Chairman Technical Committee 301, Professor Alessandro Flora, Technical Committee 301 members from all corners of the world, President Indian Geotechnical Society, Dr. Anil Joseph, President IGS, Dr. Anil Joseph, Secretary IGS, Dr. AP Singh, sir. Other technical members from ISSMGE also have joined, have registered for this particular course. Of course, our speaker, Professor Guido, distinguished faculty members, researchers, practitioners, and dear students. I welcome you all for this particular lecture series on conservation of heritage site. And today we are going to have very first lecture that will be on investigation and preservation of historic tower foundations. So I request the Technical Committee 301 Heritage Site Chairman, Professor Alessandro Flora, to say a few words.
Thank you, Dr. Chabda. Hello to everybody, and thank you for joining this first lecture of a series we are launching as a technical committee. I will just spend a couple of minutes telling you what TC301 is. It is a technical committee of the International Society of Soil Mechanics and Geotechnical Engineering, which is specifically dedicated to the preservation of heritage sites from a geotechnical point of view. And we have 47 active members from all over the world. And of course, I want to stress out that it is a peculiar technical committee. The number tells it is a peculiar committee because for our society, the 100 technical committees are the ones that deal with the fundamentals of geotechnical engineering, the 200 with the applications, with the typical geotechnical applications, and the 300 technical committees, and we are the first one, we are 301, deal with the impact on society. So our committee deals with the impact on society of the role that geotechnical engineering has in the preservation of heritage. Now, it is a difficult and complex topic. You know, we people around this virtual table know that it is a complex and multidisciplinary topic, and this is the reason why there is a need for our technical committee, because we have to spread a geotechnical culture in the preservation. As I am certain we will see in the lecture of Professor Gottardi, which I thank of being here, there is no geotechnical engineering for the preservation of historic sites, but there is an important role of our discipline. So we had the idea, and I thank Dr. Chabda, who was very active in this, of launching this series of web lectures just to share, let's say, geotechnical preservation culture in the preservation of historic sites. Also because what we have learned, you know, traveling around the world, is that there are important differences in the approach around the world. So it is really important that we discuss around the world among us on the topics to deal. Now, as I told you, the idea, Dr. Chabda has organized everything, so I really thank him as a very effective secretary of our technical committee. And the web series is will be recorded, will be on YouTube and on the website of our International Society, so you will be able to listen to it also offline. And I also, of course, thank the Indian Geotechnical Society for having supported the initiative, giving us the opportunity to meet on this Zoom meeting. And I don't want to spend any other word, and I want to invite Dr. Anil Joseph to say a few words as president of the Indian Geotechnical Society.
Yeah, very good morning, good afternoon, and good evening to all. I would like to congratulate the team of TC301, a very impactful thing, a series which is impacting the society, and it is very important. Congratulations, Professor Alexander Flora and Jidesh, to starting this program, and who other than Dr. Professor Guido to give the first lecture. Congratulations, and on a very important topic, investigation and preservation of historic towers. I have been asked to talk about Indian Geotechnical Society, and I will take the next 2-3 minutes just to share a small PPT, which will be, if you can just allow me to share. Yeah.
Yeah, please share, sir.
Yeah. So just as most of you know, but then there are people from the TC committee from different parts of the world. So a few glimpses of Indian Geotechnical Society. And it's the 7th largest country in the world with the largest population, and it is the land of harmony and diversity. And we have a lot of old structures, and definitely this TC 301, we need a lot of support to preserve our heritage, which is so diverse, and we need the help of Alexandra Flora and Professor Guido and the entire TC 301 committee to how to preserve our old heritage, which is lasting 5,000, 6,000 years. So our society was established in 1948. Now we have almost 76 years, and we have more than 6,000 members spread across 55 chapters. These are the objectives, which I don't want to go to, but then we promote conference, seminars, symposia, workshop, webinar, and annual general meeting, and also give the best local chapter award. And also we insist of promoting a lot of young geotechnical engineers, people who are below the 35 years of age, because we believe that it is the future is in them, and they are going to make the difference. We also have a journal, Indian Geotechnical Journal, which is now in the 52nd year, and also we have the IGS newsletter, which is published every quarterly. A lot of awards are given to promote engineers, and 37 best paper awards and 15 best papers for young engineers. A lot of industry awards is also given to bring industry academia close together, so that it improves the interaction, and which is very much essential, especially in case of the heritage structures. And we have a vibrant web portal, and you can go in, and all this lecture also will be uploaded into our web portal as well, so that people can get more knowledge. And also we give for the students practice software programs so that they can improve upon them. And India is quite active in this. And I just wanted to mention the 2 major events which is coming for us, 3 events in fact. Then 19 to 21 December 2024, we have the Indian Geotechnical Conference coming at Aurangabad. So I look forward for people to join that. And this is the important dates for that. And we have the first Geotech Asia coming up in Taj Sidade, Goa Horizon. I wanted Alexander Flora and Professor Guido to join us in this mega conference, which is similar to Asian Regional Conference, which is promoted by India. That will be the beautiful tourist city of India called Goa. So definitely look forward for meeting you people. And it is in collaboration with IIT Bombay. And also we have the 12th ISSMGE, that is the field monitoring in geomechanics, coming up in 2026, which will be in IIT Indore, organized by Professor Nilima Satyam, who is very active in our society. So we have a tie-up with other societies. We keep on networking and had made tie-up with many of the companies, many of the countries like United States of America, Brazil, Nepal, Sri Lanka, Japanese, Korean, and other countries. So this is all for me for regarding the Indian Geotechnical Society. And I would like to once again congratulate the organizers for coming up with this, and look forward for listening to Professor Guido regarding the preservation of the historical towers. And over to you. Thank you very much, Jidesh, for the opportunity. And thank you, Alexandra, for doing this.
Yeah, thank you, Dr. Anil Joseph, sir, for addressing the gathering and telling about Indian Geotechnical Society. Now I take this privilege in introducing the speaker, Dr. Guido Gottardi. He is Distinguished Professor of Geotechnical Engineering at University of Bologna, Italy. He holds the high school diploma in classical studies in Venice, followed by an exemplary MSc in civil engineering from University of Padova and a PhD in geotechnical engineering from Technical University of Torino. Dr. Gottardi's academic pursuits have taken him around the globe, including a period as Marie Curie Research Fellow at the British University of Southampton and Oxford, Dr. Gottardi is prolific researcher with over 150 scientific papers to his name, covering a wide range of geotechnical subjects. He has contributed significantly to professional organizations, serving as president of National Group of Geotechnical Engineering, contributing to international technical committees, and the coordinator of Italian group of academic geotechnical professors and researchers. Additionally, Dr. Gottardi provides technical support to various projects, including environmental and geotechnical monitoring, also of historic structures. His expertise and leadership have earned him recognition as a visiting professor at esteemed foreign universities and as an external reviewer for international geotechnical journals. With this very short and brief introduction of Gottardi, I invite him to deliver his first lecture, that is Investigation and Preservation of Historic Tower Foundation. Over to you, Professor Gottardi.
Thank you. Thank you very much. Let me share my screen. Okay, just let me know if you can see it.
Yes, we can see.
Okay, so thank you very much for the kind introduction, and many thanks to the Technical Committee 301 and the Indian Geotechnical Society for inviting me to deliver this initial talk of this really exciting lecture series. As you can see, I will focus on the preservation of historic towers and especially of their foundations. Now, okay. Here is a brief summary of this lecture, starting with only very few slides on the general recommended approach when dealing with the preservation of historic structures. And I will then try to demonstrate these principles by showing a couple of well-documented case histories in which I happen to be involved. They are located in two Italian cities, Bologna and Venice, where I had the fortune to grow up and live. Both cities are well known for the past presence of a very high number of towers, mainly civic towers in Bologna and bell towers in Venice. Now, our technical committee knows very well that for such a complex topic, it is not possible to provide prescription of general validity. But the TC rather aims at collecting a number of instructive examples that could be used as a source of inspiration for geotechnical engineers. So really a sort of methodological approach. And this is exactly what I mean to do here with you today. Now, I am sure we are all aware of the international guidelines on existing structures and their Annex I that points out the importance of preserving authenticity and integrity of heritage structures. In particular, of foundations that are not different from the rest of the structure as character-defining elements. And when dealing with possible interventions and remedial measures, preserving integrity requires minimal intervention, incremental approach, and possibly removable measures. Now, we all know, however, how the concept of preservation and even the definition of authenticity can be seen and interpreted in different ways around the world according to different cultural contexts. And I believe that one of the main tasks of our TC is exactly to offer a forum of discussion and debate to our geotechnical community on all such critical issues. Now, no doubt, preservation is an interdisciplinary activity, as already mentioned and we all know, and requires the contribution and the competencies of many experts that should refer and talk each other. Among these, geotechnical engineers, but all must also play a decisive role, I think, even if this is not always the case. It is in fact self-evident, even if they are not visible, foundations and the supporting soil are parts of a unique, comprehensive system for which authenticity and integrity must be preserved. The replacement of or substantial modification of the foundation structure or elements can alter or even destroy forever an historical essential feature of a monument. And towers in particular, I think, are structures whose behavior mainly relies on their interaction with soil, and therefore the solution to their possible problems could be found exactly there. Now, talking about towers, I cannot but just mention the most famous example of a respectful approach, the soil extraction intervention carried out for the Leaning Tower of Pisa, only after many years of studies and investigations, and having taken into consideration several options, following a careful step-by-step procedure and achieving the final successful result, as our good friend Professor Carlo Vigiani likes to say, without touching it. Later on, I will present you a less known case that followed a very similar approach. But let's start from the two towers in Bologna. Garisenda and Asinelli are the true symbol of the town and of its Middle Age architecture. Located one close to the other, in the very heart of the city center, they are among the few remains of a past when tens of towers used to populate and make characteristic the skyline of Bologna. Here you can see the main figures of the two towers. Garisenda, the shorter one, was constructed first towards the end of the 12th century with thick rubble masonry walls and a height that was originally 60 meters, but was soon reduced to slightly more than 48. The current height, because of its significant leaning that most probably started soon after its construction. Its current inclination towards southeast is quite impressive, and this generates an important overturning moment onto its foundations with serious critical implications on its long-term stability. At the right bottom end of the slide, you can see here with a black arrow the main direction of the inclination, both of Garisenda and of Asinelli, which is almost opposite to it. Fortunately, the Asinelli has got a much smaller inclination, but it is twice as much taller, making it the tallest and the most slender original medieval tower in Italy. It was constructed soon after the Garisenda with larger foundations and thicker walls, probably after having learned the relevant lesson from the adjacent Garisenda. Now, if we look at the historical sequence of events that concerns the two towers, one can see that while the Asinelli was raised up to more or less the current height, which is 100 meters, the Garisenda height was reduced of 12 meters, as mentioned, even if the initial idea, because of its inclination, was to demolish it completely. If you think that the two towers are located right in the city center, many events occurred over the past centuries with lots of constructions, craftsmen's workshops, even a small church here built in the area and around the towers. All these structures were demolished at the end of the 19th century. Now, it might be interesting to know that the construction method of a medieval tower remained substantially unchanged until the beginning of the last century. The main body of the foundation was essentially made of a conglomerate block cast in place, directly laying on the virgin soil or sometimes on wooden piles. The structure of the tower was made of the typical rubble masonry walls with this gravel and bricks with lime mortar inside and this external coating by masonry bricks. Now, the estimating building time, the whole tower, could be around 5 years. I think this is quite impressive from the historical documents. Another aspect to be known is the geological setting, where the historical center of Bologna is located in the Po Valley at the northern foothills of the Apennines, and its likely elevated position corresponds to the interfluvial area between the rivers Savena, here on the right-hand side, and Reno on the left-hand side. There are other small rivers and creeks flowing into the city center, and the subsoil of the Bologna city center is mainly alluvial deposits of the Pleistocene era. And as you can see, for about 100 meters below the two towers position, you have essentially fine-grained soils. And this was also, of course, found out with the several geotechnical investigation campaigns that were carried out over the last decades by the different committees that had been called upon to look after the tower. The final geotechnical investigation, it was carried out in 2016, and as you can see, it was made up of corings, downhole tests, dilatometers tests, and some geotechnical monitoring like piezometers and assistimeters. From these investigations, as well as from the previous one important feature could be reconstructed, which is how the foundation of the Garisenda Tower is made of. Because we know very little about these towers from the old documents, so we don't know even how they are made, what is the material, what is its geometry. So starting from the bottom to the top, we find a foundation block made of conglomerate and lime mortar as well. Then a basement made in selenite stones. Selenite is a local gypsum rock which is much used locally in Bologna for many historic buildings. And then the basement of the tower is made now with external walls in selenite stones, but an internal mixture of lime mortar, river gravel, and shards of bricks, what we call the rubble conglomerate, that we can find also on top of the structure, where instead of the selenite stones, you have the masonry bricks. Now, this is what a preliminary geotechnical model that we could devise from for example, the boreholes and the piezocone test. Now, the positional environment was over the centuries and the era, the past era was quite homogeneous, and the material is essentially an alternation of clay soils and silty clay horizons. But especially in the first 10 meters, which from 5 to 15 meters depth, which is the depth which is of most interest for the tower foundations, you can find a high dispersion of geotechnical parameters. So in the attempt of getting to a refined geotechnical model to reduce the uncertainty and the dispersion of those parameters, we tried to look into these alluvial deposits that for their nature show typical lenticular geometries with very poor lateral extent, and they are locally interrupted by paleosols. What are paleosols? Paleosols are post-depositional phenomena that typically develop during a long period of subaerial exposure of topsoil. So you can find in time this sequence of horizons, A, B, and BW, with a different degree of pedogenesis. And this is the reason of an important lack of uniformity, both vertically and horizontally, which was found in a small area, like only the size of the square with the two towers. But if we try from the investigation to reconstruct this post-depositional phenomena and try to interpret from the investigations, then you can end up with a much more refined geotechnical model like the one you can see here. Now, I won't go into the details of this very articulated model, but we could actually reconstruct the different layers, ascribing them to their history, and so much reducing the uncertainty of their geotechnical parameters. So in this way, also the stratigraphy of the local subsoil could be reconstructed in a very detailed and reliable way. If you look at this picture, for example, radiocarbon datation on the horizons which were richer in organic content, the ones who were exposed to the subaerial exposition, in fact, then we could confirm the stratigraphy based on the paleosolar reconstruction. And from this picture, you see that we were able to find in the subsoil also the footprints of the two towers due to their strong settlements over the centuries. That was more or less estimated between 1 meter and 1.5 meters as total settlement of the two towers. Another interesting aspect was that following the post-depositional processes, we could find a local heterogeneity on the left-hand side of the tower here, only for this piezo cone test that you can see on the top right side. I don't know if the picture is covered by my picture. Anyway, this red arrow indicates a piezo cone test which was carried out exactly on the leaning side of the Garisenda. And this could be the reason of the initial leaning of the tower, the fact that there is this weaker layer of soil right on that side. Of course, this is only an assumption, difficult to demonstrate, but this is consistent with the fact that the tower started to lean soon after its construction. So this makes the overall framework of knowledge and understanding of the situation of the foundation and the subsoil below the foundation for the Garisenda, because a refined geotechnical model is required to reliably investigate a possible leaning instability mechanism that we know very well for the much inclined, very leaning towers, that is due to lack of stiffness of the foundation soil, not of the strength of the soil. And this was the result of the continuous ongoing increase of something which is an already alarmingly large inclination of the tower. However, in this moment, more urgent structural issues arose for the Garisenda and are related to the extremely high stress level, which again, because of its strong high inclination, exists at the southeast corner of its basement, and at the same time to the progressive degradation and the gradual local disintegration of the selenite stones. So this main concern required and is still underway a careful, extensive, real-time monitoring and analysis to improve the present understanding of the tower behavior and devise possible interventions to reduce the risk of collapse. So I will now show just a few slides on the structural aspects of the Garisenda, starting from the very articulated and extensive monitoring systems that was implemented in the Garisenda over the years. So on the upper portion of the tower, extensometers, strain gauges, short and long base deformeters, and so on. In the basement of the tower, more recently, because of the problems detected, inner optic fiber sensors, acoustic emission sensors, wire strain gauges, and a long inner pendulum. Now, from all this monitoring system, it was quite clear that something, an anomalous local deformation was occurring at the basement of the tower. you can see that a settlement, a differential settlement of 0.24 millimeter per year was detected and on top of the basement, whereas the foundations showed a differential settlement of much less than that. So the tower is no longer rotating rigidly around its foundations, and this is definitely a critical issue. Remember, this is a cross section of the basement. Remember that the inner part is made out of rubble conglomerate, and the rubble conglomerate is contained by selenite blocks. Now, an additional complication of the basement is that the outer selenite blocks are covered these days by an additional selenite cladding, which was added at the end of 19th century. Remember, after the demolition of all the shops and churches which had been built around the tower, mainly for aesthetical reasons, this is what we call the bugnato. Now, this is, of course, prevents us to check the state of preservation of the outer selenite blocks. And so this is a lack of knowledge on these days, which is very, very important. Now, this is a picture which was recently taken inside the tower, and this is the southeast corner of the tower, where you have the largest inclination of the tower. And exactly on that corner, you have this area where the selenite blocks were seriously altered because of exposition to very high temperature in the past, because of reported fires, very important fires in the 14th and in the 17th centuries, and also possibly to the presence of forges that are reported in historical documents until the 19th century. Together with a current high level of humidity, this leads to a gradual local disintegration of the selenite stones, which has now reached a reduction of the regional thickness up to about 20 centimeters, exactly in the angle where the stress level is highest. Now, because of that, this was also confirmed by the fact that the cladding was bowing outside, and this was also detected by laser scanning. And this supported the alarming hypothesis that the cladding had started to contribute to the tower statics, and it was prone to local instability. So what the committee decided to do as a counteraction was first to reduce the risks of the sudden collapse of the basement of the tower, introducing a passive confinement of the tower basement, an active confinement of the tower corners, and an active confinement of the cladding, all interventions which were already carried out. Still, these interventions did not reveal fully successful, and the current concern, as I said, is on the basement structure of the Garisenda. And there is a great, because of the uncertainties on the materials and on the preservation of such materials, there is a great uncertainty on the actual safety margins of the towers. The critical situation, the existence of a critical situation, however, is well established, and it is kept under constant monitoring, real-time system. Due to their position in the city center and to the very high exposition, however, the tower there are unacceptable risks for these reasons, and safety requirements were implemented prior to any further strengthening interventions. And in fact, a safety all-around sort of belt to protect adjacent historic buildings from possible tower collapse were designed and put in place. Now we can show you a rendering of the design of all this sort of structural belt all around the Garisenda Tower, and another picture, and now a picture of the of these caissons put in place. This is dated back, has been completed, and the story, the Garisenda story of preservation and strengthening is far to be completed. It's still under investigation, and this will be developed in the next decades. You see how the complex situation requires challenge and innovative situation, which are not always an immediate to find out. Now, here you can, I have reported a few references on the topic, which I have produced with my research group, Michela Marchi and Ilaria Bertolini, in principle. Now, let's move to the second case history that I want to tell you about, and is concerned about the Basilica of Santa Maria Gloriosa dei Frari in Venice. And the Basilica, as you can see from this picture, is a classic and most splendid example on Franciscan Gothic style. It looks nowadays exactly as it used to look many centuries ago, as you can see from one of the bird's eye prints that you can find in the historical Venetian documents. So in Venice, everything is almost almost more or less the same. Now, I like to show you just a picture of the interior, just because the magnificent interior, which is of the church of the Basilica, which is more than 100 meters long. But now let's move to the Venetian subsoil, which is mainly made of alluvial deposits of the Quaternary Basin, and the first 10 meters are recent lagoon deposits made up out of soft clay and silty clay with organic content, shells, everything inside. And as you can see, this layer, which supports most of the historic foundations in Venice, is quite weak, with an undrained shear strength, which is around 30-40 kPa. So quite a challenge for the Venetian ancient engineers when you have to build very heavy buildings like bell towers. Now you can see the reconstruction of the bell tower foundation of San Marco, which is made from top to the bottom of Istrian limestone block, then a quite heavy and thick wooden boarding, and then short but very efficient compaction piles driven into this that soft silty clay layer. Now, how do we know about this perfect geometry of the San Marco bell tower? Because San Marco bell tower in 1902 suddenly collapsed and fell down. This is quite a well-known case history. The San Marco bell tower was then reconstructed soon after, exactly as it was and where it was. So beware if you go to Venice and visit San Marco Square. San Marco bell tower is a sort of a fake. It's probably one of the only fakes in Venice. It dates only 100 years. But anyway, before reconstructing it, it was possible to check its foundations and understand how they were built at the times. Now, after the collapse of the bell tower, of the San Marco bell tower, all the other bell towers in Venice, but I would say all the other towers in Italy were subjected to a careful inspection, and especially the Frari bell tower, which is the second tallest bell tower in Venice. constructed in the second part of the 14th century in Romanesque style. Now, it's quite an interesting story that a smaller primitive church was built in 1225 by the Friars Minor, and the bell towers was designed, as all bell towers at the time, as a separate independent structures, because bell towers are heavier and subjected to greater settlements with respect to the church, the nearby church. But due to the growing demand, works soon started again on its much larger replacement, which is what you can see in this old picture, but also you can see today. The present basilica has got the main axis reversed and incorporated the bell tower in the masonry walls. If you look at the plan view of the basilica, you can see here circled in red that the bell tower is now part of the basilica structure. And this, of course, over the centuries provided several problems because of differential settlements. Now let's have a look at the tower, which is a double brick masonry structure. The height is 65 meters and the base width is between 9.2 and 9.4 meters. The weight is about 57 meganewtons, with a moment which is not as large as what we have seen for the leaning towers in Bologna. And in fact, the inclination is not that much concern. The main concern here is not the high inclination, but the interaction with the basilica structure. And especially because after the San Marco bell tower collapse in 1904, a main strengthening intervention, enlarging the foundations, was carried out only on this side, on the leaning side of this bell tower. Now, this asymmetry led to problems of interaction between the tower and the church and the basilica. If we start from the initial situation with the bell tower incorporated in the masonry walls of the basilica, over the centuries, the tower showed a differential settlement relative to the basilica, and this produced a out of plomb towards southeast. Now, at the end of the 20th century, differential settlements of about 40 centimeters was recorded. But after the intervention in 1904, the tower started tilting in the opposite direction towards the basilica because of the intervention here at the bottom side, which is I am highlighting right now. And still there is an average settlement of 1 millimeter per year, 10 centimeters in 100 years, so which is quite relevant after so long. Now, what are the consequences of such differential settlements? You can see if the structures are connected. You can see here in the arch inside the basilica, you can see the cracks on the left aisle walls, but this big diagonal crack on the brick masonry structure is not due to the differential settlements. This is due to the fact that the tower is going towards the structure of the basilica. And this, of course, is a great concern for the stability of the structures themselves. And at the time, we carried out flat jack measurements showing the presence of a thrust line on this very slender and delicate column of the basilica, with measured stress levels which were quite close to the resistance, to the strength of the column material. So something had to be done to reduce this very harmful interaction. But there were requirements on this intervention, of course, trying to not to completely stop the settlements, just limiting the differential settlements between the basilica and the bell tower, preserving as much as possible the original foundation structure. We know that integrity and preserving the authenticity. Now, essentially avoiding to propose a rigid foundation system for the bell tower. In one word, avoiding micropiles to stabilize the tower. And also enabling a flexible and modular intervention according to the outcome of a suitably implemented real-time monitoring. So now what we started, of course, from geotechnical investigations that were carried out all around the bell tower and inside it. And these geotechnical investigations were made of boreholes, piezo-cone test, dilatometer test at various stages of the intervention. This is a picture of an inclined borehole from which you can also determine the foundation block, which, as you can see here, is made of Istrian limestone. Then you have the piles, the wooden piles, and then the soil, the clay, silty clay soil beneath the piles. You can see the entrance, now the current entrance to the bell tower, which is more than 50 centimeters down with respect to the ground level. So you have to go down a couple of steps to enter into the tower. Now, this is the foundation soil profile which we came out with after the geotechnical investigations. And so you can see that the compaction piles built at the time were very short and not able to reach the sandy soil below. This is the intervention made in 1904 with longer piles, which represented a sort of a pin for the rotation of the tower. Now, because of these very soft clay layers, which is trapped between the piles and the stronger sandy layer, this silty soil layers tends to be squeezed out and to continue produce the settlements that we measured in 1 millimeter per year. So this was the mechanism we had to prevent with intervention. So what was the strategy of the intervention? First, a provisional strengthening intervention with a steel cable, trying to bear a part of the horizontal thrust. And then the main intervention was via soil fracturing. Soil fracturing means injecting the soil, producing fractures, and filling them with grout. In the end, you will build a sort of a belt around the foundation of the tower of improved material, which should prevent the squeezing out of the silty clay here and allowing the tower to go to settle vertically without any interaction with the basilica outside. So quite an innovative intervention, and once again, without touching the tower foundations, so fully preserving their integrity. At the end, a structural joint could be carried out in order to separate the two structures and reduce the damaging interaction between the different masonry structures. So the soil fracture intervention was designed all around the foundation, was preceded by a test site to check the feasibility and the optimization of the injection parameters and the grout properties. Here you can see that 88 pipes were inserted around the tower along 2-3 rows at a spacing of 50 centimeters, and the grout injected from 21 valves spaced at 50 centimeters each other. These are a couple of pictures of the intervention in a very delicate and difficult to operate environment inside the church. Now, all the intervention was followed by and kept under constant real-time monitoring of grout injection parameters, of the soil behavior, and of the bell tower. In particular, for the soil behavior, piezometers, extensometers, and inclinometers were carried out around the tower, together with boreholes, piezocone and dilatometer tests, which were carried out at various stages of the intervention. So let me just show you a couple of this large amount of data. And for example, from the piezometry data, all this sudden increase, these spikes, could be recorded, corresponded to the injection phases from the valves near the piezometers. But what we could see that immediately after the sudden rise because of the injection, there was a sudden decrease due to the consolidation of the excess of the pore pressure excess. And so we could realize that there was a relatively quick consolidation rate of our silty clay. And this was quite reassuring for the control of the full intervention. Another interesting thing that we found out after the intervention from the samples extracted, that we could actually see the lengths of grout that we had injected in several phases. So we could realize that the soil had been fractured and the fracture had been filled with grouts, which is not exactly what you could see in the textbooks, but it revealed successful anyway, especially if you compare piezocone and dilatometers tests before and after the intervention. Also during the intervention, you can see that both strength and stiffness of the soil have improved because of the grout injected and the soil compressed between the grouts. Now, to complete this presentation, let me show the precision leveling that provided before the intervention a differential settlement between the tower here at the bottom left and the column of the basilica of about 1 millimeter per year, as mentioned. During the intervention, this was increased to 5 millimeter per year, so quite a big concern. But after the intervention proved to be successful because it was reduced only to 0.27 millimeter per year. Now, of course, after the structural joint, the differential settlement increased because of the structural joint, but because of its presence, the interaction was definitely less harmful. So in the end, we can say from this case study, but in general, we have to stress the crucial role, as I hope to have shown you, of the interdisciplinary investigations when we deal with this type of problems. So we have to go through history, architecture, materials, geology. Of course, geotechnical and structural engineering should be considered and can give their important contributions. And then we have to try to think innovative criteria and methodologies to apply to the foundation and the structures, and thinking of a step-by-step intervention. In the case of the Ferrari Bell Tower, as in the Pisa Tower, the foundation material was fully preserved, and an articulated and extensive real-time monitoring system allowed to calibrate and minimize the amount of intervention, which is, as we said at the beginning of the lecture, from the guidelines. A flexible technique was devised, enabling and adjusting further interventions if required. Now, again, a list of references on the topic from myself and my research group. And let me just conclude reporting a very nice quotation taken from the book that I'm sure all of you of our technical committee knows very well, Geotechnics and Heritage Historic Towers. In the introduction, provided by famous Italian art historians, there is a nice quotation on the importance of towers. Thank you very much for your attention.
Thank you very much, Guido, for your brilliant lecture, which I really appreciated, and highlights the relevance of investigation and monitoring, because one of the key issues is that we do not know exactly how the structure is, what is there, and what are the safety factors. So you clearly demonstrated that. Now, Jitesh, please, now the word to you if there are any questions. I think there is one already.
Yeah. Dear participants, if you have any questions, please unmute yourself and you may please ask to the speaker, Professor Guido.
I think there is one written question. Is a CPT and SPT results correlation made by some Gallian, I think. I think they're asking what kind of correlations you used, I guess.
Yes, actually, I have shown CPT data and DMT data mainly on this very soft soil. These, I believe, are the main investigation tools, providing interesting information on the strength and the stiffness of the soil. We did not carry out any SPT test in this case. They are, as you know, less reliable, especially in fine grain materials. So there is no correlation actually that I made use of between SPT and CPT. But I tried to put together always CPT and DMT, and there is quite a good cross correlation of information from the two types of tests.
Yeah. Is there any questions from the participants? Okay. Since there are no questions, so we can end the session here.
Yeah, before we end the session, Jitesh, allow me to remind to all the attendees that there is a brand new website of our technical committee, which is TC 301. If you write TC 301 historic sites, you will find it, where we have put some references from literature. There are news on the conferences around the world that are of interest for the preservation of historic sites. So please take a look to the website and let's try to keep it alive. So inform us of any kind of activity going on that may be of interest for the community, and we will publish on the website. So thank you. Jitesh, go ahead.
Yeah, I have posted that link in the chat box. So those who are interested, please go through that particular link. Yeah, so let me, first of all, I would like to thank the Professor Guido Gottardi to deliver the first lecture in this lecture series on conservation of heritage sites. I thank Chairman TC 301, Professor Alessandro Flora, and the technical committee members 301 to support this lecture series. I thank President Indian Geotechnical Society for addressing the gathering and the support what they have provided for this particular lecture series. Finally, I thank the dignitaries, those who have joined for this lecture series, and the participants for attending this lecture series. We will make the announcement of the lecture number 2, that is on conservation of heritage sites, soon. So thank you one and all for participating for this particular lecture series. Now I request all the participants, if they're able to turn on their video so that we can take one group photo. Yeah, if everyone can please turn on their camera. So I'll take a couple of screenshots. Yeah. Yeah, with a smile on the face, please.
Do you have all of them on the same screen?
Yeah, I think I need to take a couple of photos. I'll do that. Yeah, I have taken the photos. So thank you one and all for attending this event.
Yeah, very informative.
Yeah, thank you, Hitesh Bhai, for attending this lecture.
Okay, thank you, and see you for the next one. Thank you again, Professor Gottardi.
Thanks to you, and bye, everybody.
Bye.
Thank you. Thank you. We will wait for the second lecture.
Thank you.
Thank you.